When you eat food, there's much more to food than just the taste. In addition to the taste, there's the texture, the way the food feels in your mouth. As a good example, this steak that we have here. We're going to cook the steak, and I'm going to show you how it feels, how the way it feels changes when you cook it. What that means is when you chew on the steak, how it feels when you chew on it changes. That's the texture, that's the mouthfeel. And that's determined by the elasticity of the steak. The elasticity of the steak will increase as it becomes more difficult to chew, as we cook it for a longer period of time. So all foods have a texture. All foods have a mouthfeel. If you don't like steak, for example, if you prefer tofu, if you're a vegetarian, it too comes in different flavors. It comes in different styles. You can get a firm tofu or you can get a soft tofu. A firm tofu takes more force from your mouth to chew it. It's more elastic. It's stiffer. A soft tofu is much softer. It's much easier to chew. And when you finish the steak and your tofu, you have dessert, you have chocolate. It too comes with different textures. Chocolate mousse, it's light, it's airy. It's very easy to chew. It's a very low elastic material. The elasticity of chocolate mousse is very low. If you take a chocolate bar, it's stiffer. It takes more force to chew it. Its elasticity increases. And if you take real chunk chocolate, or really good Belgian chocolate, it's much stiffer. You have to bite much harder. So the mouthfeel, how it tastes, all is wrapped up in the elasticity of a food. And this is how we characterize what the mouthfeel of a food is. So if we want to measure it, we have to measure the elasticity. And let's start with the very simplest thing. Let's start with a spring. Here I have a spring, and I can hang a weight on the end of the spring. If I hang a weight on the end of the spring lengthens. It becomes longer. It becomes longer by a certain amount. That amount, that delta L, the change in length, is determined by how stiff, by how elastic the spring is, and how large the weight is. So let me hang the weight on it. The spring gets longer, but then it stops moving. The forces are balanced. There's no longer a net force on the spring. The spring is exerting a force to hold the weight up, and the weight is exerting a force to stretch the spring. We can do the same thing if instead of lengthening the spring, we compress the spring. We put the weight on top of the spring, like this. If you push on the spring and you push it down, then the spring pushes upwards. It pushes in the opposite direction. It tries to bring itself back to its original length. And we can write the relationship between the force of the spring and the change in the length of the spring. It's called Hooke's law, and it just says that the force is linearly proportional to the change in length. This minus sign arises because there is always a restoring force. The spring is always trying to retain its original length. It's trying to get longer if you're compressing it, and it's trying to get shorter if you're extending it. The relationship between the change in length and the force is the spring constant, and that determines the elasticity of the spring. The larger the spring constant is, the more the force it takes to extend it by a given length. So a stiff spring has a very large spring constant, and it takes a larger force to extend it. We can use the same concept now to describe food. In the case of food, we have some object. For example, we have this piece of steak. We want to measure the elasticity of a piece of steak. The force that we put on the food, the force that we put on the steak, will depend on the size of the steak. So if I take a very large piece of steak and I want to deform it, I want to squeeze it, I want to change its thickness by a certain amount, it takes a much larger force than if I take a small piece of steak. But when I tell you what the elasticity of the steak is, I don't want to have the dimensions of the object, of the piece of steak, as part of the elasticity. So I want to somehow take out the dimensions of the steak. So to do that, I take the force and I normalize the force by the area on which I apply the force. That gives me the stress. The same point, I don't want to know how thick the steak is when I compress it. I just want to know how much I compress it for a given thickness. So I take the compression, I take the change in thickness as I squeeze on the steak, and I normalize it by the original length. And that gives me a strain. A strain is the relative change in length. Now I can calculate the elastic constant in the same way that I calculated the spring constant. I want to calculate a spring constant, I take a force and I divide it by a change in length. For the elastic constant of the steak, I take the stress, which is the force divided by the area, and I divide that by the strain, which is the relative change in length. And that gives me the elastic constant of the food.